It seems as though in the last few years we hear words like nanoparticles and nanotechnology more and more, but if you are anything like me, you might be wondering what exactly these words mean and why they're so special. So today I will try and explain a little bit more about why these are being so thoroughly explored. What does this mean? Well, nanotechnology pertains to the use of materials and devices on the scale of the size of atoms or small groups of atoms. The nanoscale is usually measured in nanometers, which I hope you've learned by now is billionth of a meter. A nanoparticle and other nanomaterials will typically be less than 100 nanometers. As you can see in this graphic, this is on the same order as the size of a typical protein. This brings me to another important point. Although we consider nanotechnology to be a relatively new area of study, we must remember that nature has utilized nanotechnologies for far longer. Much of the enzymatic and catalytic machinery that makes life possible has existed for billions of years without us knowing. Materials on the nanoscale have such unique properties due to two major reasons. As we learn in quantum mechanics, as the size of something gets bigger, its quantum character begins to disappear. It just so happens that on the nanoscale, the dimensions are in the same range of wavelengths as the fundamental excitations of materials such as electrons, photons, phonons, and magnons. As we saw, electron wave functions are often between 10 to 100 nanometers. Because the size of nanomaterials is comparable to these, the way the excitations move through the material is affected, giving nanomaterials the unique properties that make them so useful. Some nanotechnology makes use of tunneling, for instance, in engineering semiconductor devices. Photonic propagation can also be altered and controlled with quantum mechanical principles. A second reason nanomaterials have so many useful properties is simply because of their large surface area to volume ratio. This means that up to half of the atoms in a nanoparticle are surface atoms, and many properties are no longer determined by bulk phenomena. For example, catalytic materials at the nanoscale will have more chemical activity per atom of exposed surface. Because nanomaterials have these two very important attributes, some very unique properties emerge. Materials on the nanoscale have varying magnetic behavior based on their size, unique mechanical properties, and unique chemical reactivity. Magnetic nanoclusters have a single magnetic domain at smaller sizes of only a few nanometers. Magnetic spins on each atom couple strongly to produce a giant single spin. In some cases, this might lead to superparamagnetism. Nanomaterials can also become extremely strong mechanically. For instance, a carbon nanotube can be created, which is extremely strong and stiff along its longitudinal axis. As I've alluded to, there are nearly limitless applications of nanotechnology that are currently being investigated. Many of these involve healthcare, and it is very exciting to see where this technology will take us in the future. One major area being investigated involves utilizing nanoparticles for drug delivery. Many of the drugs that are currently being developed are not water-soluble, and thus drug delivery becomes difficult. However, this barrier can be overcome with nano-sized particles. An even more exciting area in which nanotechnology may aid in drug delivery is in targeted release. The drug will be attached to a nanoparticle, and it can be controlled to release the drug over an extended period of time or when triggered to do so. The surfaces of the nanoparticles can be engineered to seek out and localize at a specific site. This could be especially useful in treating things like cancer, where it is extremely advantageous to only affect the diseased site. Researchers are also working to develop dendrimers that can alter their cavity sizes specific to the drug being delivered, and upon reaching specifically targeted molecules, they would swell and release the drug. Nanoparticles might also become especially useful in diagnostic medicine. These would be targeted to detect specific biological signatures through a bioassay. A fluorescing dye molecule would be then attached to the target molecule to reveal its concentration. Another approach would use semiconductor nanoparticles that fluoresce at different wavelengths depending on their size, which would allow different receptors to be essentially tagged with different colors. Finally, magnetic nanoparticles might also be used by attaching them to antibodies. When they are free, they will rotate rapidly, but if the antibody has bound to its target, it will not rotate freely and will give a distinct signal. A third major area of research involves utilizing nanotechnology to create devices to assist people who have lost natural capabilities. One such application involves the engineering of retinal implants for those who have lost their vision using photodetector arrays which transmit signals from the retina to the brain along the optic nerve. Nanotechnology might also be used in tissue engineering, and the list goes on and on. As you can imagine, the list of biomedical applications I have presented here is by no means comprehensive, and the ways this technology might be applied will surely multiply in years to come. It is also no surprise that there are a huge number of applications for nanotechnology in electronics. Quantum effects such as tunneling will eventually limit how small our conventional electronic devices can be made, and thus nanotechnology must eventually be utilized if we are to continue packing more and more information into the same amount of space or making things even smaller than they are now. As I discussed briefly earlier, carbon nanotubes have some remarkable properties. Depending on the size and bonding arrangement of the carbon atoms, nanotubes can either act as metals or semiconductors. A wire made from a perfect nanotube, also known as a nanowire, has the capability to carry a lot more current than a traditional metal wire of the same size. Transistors can also be created using nanoscale technology. The energy required to add a single electron to an isolated physical region becomes significant through barriers like a tunneling barrier. Currently, however, this technology is only useful at lower temperatures because the size must be reduced to a single nanometer for room temperature applications. Currently, electronics use electric charge of the carriers to perform logic operations. However, with the use of spintronics, the spin of electrons, meaning whether they're spin up or down, might also be used to carry information. Finally, nanotechnology offers ways to make information storage even smaller, thus allowing for even greater storage capacity in a smaller space. There are several ways of doing this that are being explored, but this is probably more information than is necessary for this legacy project, and I'm sure it will continue to change in the next few years. So we use that thing called Google. Alright, but all joking aside, the last application of nanotechnology I will discuss is in communications. Optical devices are being structured in order to lead to advances in communications technology. One optical device being explored is the vertical cavity surface emitting laser, which contains quantum wells that confine charge carriers in well-defined regions to provide a way to convert energy into the desired wavelengths of light. Other optical devices include quantum dot lasers and photonic crystal materials. So I've discussed some of the basic aspects of nanotechnology and why it is so special, but as I have already said, and I'm sure you can imagine, this barely scratches the surface. I obtained most of my information through the Britannica article on nanotechnology, and for more information on the things I talked about specifically and a few I did not, this is a great source to look at. Otherwise, as I'm sure you've found out previously or discovered on your own, Academic Search Premier will get you a ton of information, and it's certainly not lacking on this topic specifically. Finally, as I talked about earlier, when all else fails, Google is your friend, especially for some of the more basic information. Alright, so we'll leave it at that, and I hope this has helped you to understand a little bit more about nanotechnology.